Okay, so hello and welcome. Last time we had our seat work. So today we're going to discuss the solutions to this previous seat work. So first we have here a bar that is supported by a hinge at E and another support out of the cable CD. So cable CD is situated at the midspan of this 8 feet length bar. And then we also have here the loading at the end of the bar AB. So first, if the allowable stress in the 1-inch diameter cable CD is 12,000 psi, determine the heaviest weight of bar AB that can be placed in the system. Okay, so for the first unknown, we're going to work with the weight of this bar under the premises of allowable of CD, which is only limited to 12,000 pounds per square inches. So moving on to the solution, of course, the first thing to do is to establish your free body diagram. Say if this is the 8 feet long bar AB, say let us label this one, this AB. So this is a weight. Of course, the weight will be situated on the mid span of this. Say this is the weight here, W. Okay. And then we also have the 450-pound block hanged at point B. So this is 450. And of course, there will be a tensile load here. Okay. Say this is tension. So I'm gonna name this as tension CD. And at A, we have a pin connection. So a pin connection will be having a vertical, say RAY, and RAX. So in this case, we'll just be concerned with W. So before we can solve for W, of course, we need to substitute the capacity of CD, okay, by using the simple formula. Say simple formula is simply equal to P over E, and then our allowable sigma is 12,000. So the P of CD, so actually we are going to apply this one for the cable, okay, so that the actual force here is actually the tension at CD, and then the area, since this is a cable with a 1-inch diameter, so of course we'll be dealing with the cross-sectional of circular section, so that will be pi over 4 times 1 squared. So we can get right away the value of CD, which is equal to 9,424.77. So this is actually pounds. So this is the capacity of the tensile load at CD. So meaning the weight should be computed wherein the limit is this value, or 9,424.77. So we can do that by taking moments at A. Of course, it's obvious that we're going to take moments at A because taking moments at A, RAX and RAY will be out of the are out of the picture. So of course we will be concerned with the distances here. Say this is 4 feet and that is 4 feet. So by summation moments at A, so first we will have the W, that is W is a clockwise rotation times the 4 distance of W from A, and then CD has a vertical component as well as horizontal component. Of course, horizontal component will have no moment arm, so this is TCDY. So only TCDY will have its moment arm. So in this case, we need to establish the slope or some of the angles. Perhaps we can tag this as our reference angle, say theta. So theta is actually the slope of the TCD force. And as we can see, if we're concerned with the TCDY, TCDY is actually opposite your reference angle theta. Okay, so we can just see if we deal with the opposite, so the function is sine. So therefore, this is equal to TCD sine of theta. So TCDY is in terms of TCD. Okay, so we determine the value of sine theta. Notice that we have here 3 vertical, 4 horizontal. Of course, we will yield to a 5 hypotenuse of this slope. So we have a 3, 4, 5 triangle as the slope of that diagonal force CD. So by that, we can now have sine theta to be equal to, see, this is the angle, opposite over hypotenuse, opposite to that angle is 3, and the hypotenuse is 5. So TCDY is 3/5 of TCD. Okay, so we will now include that in our moment, and it will cause a counterclockwise rotation. So we're going to indicate that by a negative sign. So therefore, this is 3/5 of TCD, or actually this is TCDY times its moment arm from point E. Okay, so we multiply that by 4. Then next, we have here 450 times 8, and all of this will now be equal to 0. Okay, so we're concerned with W here. So this time we are going to consider the limit computed from its allowable and the cross-sectional area. So we'll just have to substitute this one directly. So 424.77. So as we can see, we can compute right away the value of W, which is 6,554.87 pounds. Okay, sorry, so perhaps we can correct this. So we have 4,754.87 pounds for the W. So the first requirement is now obtained. Okay, so moving on to the second requirement. Okay, perhaps we can clear some of the solution here. Okay, so if bar AB weighs 21,719.47, determine the minimum diameter of the cable CD that is limited to 12,000 psi tensile stress. So this time our W is given. Okay, so perhaps we can write that one. Say we have here 21,719.47 47 pounds. Okay, and then determine the minimum diameter of the cable. So therefore, if we're going to have this formula being applied to CD, area here is not yet known, so therefore we will be concerned with the value of the tensile at CD. So because if we simplify this is actually sigma of CD and then tension at CD and the area. So after getting the area, we can now determine what will be the required cable diameter if it is limited to 12,000 psi considering this weight. Okay, so we can do that again by taking moments at A. Okay, summation moments at A is equal to 0. First, we have the weight that will be clockwise, 4, and then the vertical component of CD, that will be a counterclockwise moment, TCDY, which is TCD sine theta, and then times the moment arm, of course that is obviously 4, and then we have here the weight, the far end. So the far end distance is 8, and this will now be equal to 0. Okay, so what can we get here now? Actually, we're getting this TCD. However, sine theta is actually known, be equal to 3/5. Okay, so by substituting that, we can have the value for TCD on the equation. So here we will be having an answer of 37,699.12 pounds. Okay, so our next step is, of course, to proceed with this equation. So here the allowable for cable CD is 12,000. So this is equal to 37,699.12 all over the circular area. And actually we are getting the diameter, the required diameter of the cable. So in here we can directly solve for the diameter, and it will yield us to a value of 2 inches. Okay, so this is it for the one of the problem of your seat work. So the first unknown, the weight of bar AB under a allowable of 12,000 and 1 inch diameter cable CD will yield to this value, 4,754.87, and then the required diameter, okay, as the second requirement, the same allowable 12,000 going to compute for the required diameter if our bar weight is pegged to 21,719.47. Okay, so moving on to the next problem, we can see here a system of forces wherein this bar is actually supported on the wall by a pin connection at A. Of course, a pin connection will tend to swing this along the rotation caused by a pin connection at A, and then out of this, the certain angle is inclined, or this is in a diagonal position, horizontal cable CD is placed, then again it is attached on C. Along this bar shall carry a cylinder, okay, placed 2 meters from A, okay, and bar AB is having a total length of 5 meters, okay. So the distance between A and C is 4 meters here. Okay, so if the cylinder in the system shown weighs 1,500 kilograms, determine the tensile stress in the 20 millimeter diameter cable, assuming a 300 kilogram weight of the bar. So what we'll do here is get the free body diagram. Okay, we're gonna start with the free body diagram of a certain object where the loading is coming from, and obviously that will emanate from our cylinder. Okay, so from this cylinder, of course, as usual, we are going to have an x and y axis. Okay, we're gonna baptize this object in the x and y axis and determine the forces. So, and of course, this cylinder is actually resting on this wall, and the wall will have a reaction, okay, towards the cylinder. Okay, so I'm gonna name this as N, or a normal reaction of the wall, and then of course this cylinder is also resting on the inclined member here. That is why the reaction of the bar to that of the cylinder is also towards, okay, towards your cylinder. Say I'm gonna term this as force P. Okay, and then what else? Of course, this cylinder has a weight. The weight is always vertically downwards. See, that is W. So in fact, we come up with force system under concurrent force system because all of the forces will eventually meet at a common point. Okay, and it so happened that this is our point of origin of this established x and y axis. So as usual, we're just limited to these equilibrium equations here. Okay, so we cannot further use moments here since we have no moment arm. So the usage of this will be also dependent to what we need. Of course, it is not unnecessary here that we're gonna perform this. Okay, we'll cross that out. So our concern is just the summation or the forces along y. Why is that? Because we are actually getting here W. So we are not concerned with the normal force here because by action and reaction, this normal force will just be transferred to the wall, okay? And we are not concerned with the wall, okay? So our point of concern is actually P. Why P? Because P will eventually transfer, okay, to your bar, okay? So it will transfer to your bar, and if this P is obtained on this free body diagram, of course, we note that there is a reaction here since this is a pin connection, say RAX and RAY. Again, this is not our point of concern, and this could be easily eliminated or out of the picture by taking moments at that point. And then our concern really is to involve cable or the force in the internal cable BC. Okay, so this is actually cable BC. So that is the sequence of our solution here. Okay, so we're gonna perform this at the cylinder at the FVD of the cylinder. So we'll have summation forces along y is equal to 0. So what are the y components? Of course, n here is exactly coinciding the horizontal. It's only w and p. So p should have a vertical component. Say this is the vertical component. Say py and px. So our concern is just py here. So of course, to establish that py, we need to have an angle, reference angle. So perhaps we can name a reference angle. Say this is the reference angle, beta. So where shall we get beta here? Of course, that could be established by this principle in geometry. So actually, I am frequently introducing this principle in geometry. A simple principle wherein an inclined angle, okay, an inclined member or surface having an angle referred to the horizontal or the x-axis. All you have to remember is just to draw a perpendicular line, okay, and the vertical line. That's it. Perpendicular to the surface and the vertical line. So vertical line is always a vertical line. Then this will be also theta. So very basic. By this simple principle, you can apply that in many cases, especially in analysis of structures. So in this case, we're going to find here an inclined member. So of course, this is the inclined member. Perhaps we can draw a horizontal line here, and then this is theta. Okay, remember that the surface of this point between the cylinder and the bar is a tangent line on a circle, and a tangent line on a circle, okay, is also always perpendicular when it is projected on the center. So whether this is your line, project it to the center, that will always be perpendicular. Remember that, okay? So whether this is your line, tangent line, touching this, project it to the center, this line is always perpendicular. So wherever it is, so whether it is touching this point, okay, say this is a tangent line, project it to the center, that is always perpendicular. Now applying that principle, therefore P here is simply perpendicular to this member, and under that condition, combining this perpendicular line to a vertical line will have the same angle. Okay, so again we will go back to this inclined horizontal theta, perpendicular and a vertical, perpendicular, this is the perpendicular, and a vertical, this is also theta actually, or we can replace this by this angle beta. Okay, that is the application of this. Okay, so if that is now established, we will find a way to express beta in a certain numerical values or degree, angle, or it could be radians, or you may just refer to the vertical and horizontal slope. So where's that? So just refer to the figure and look at the dimensions. So of course, if we have to project this, okay, the dimension is already given, and how much is this? 5 actually. This is 5. And of course, this is 4. And we are actually dealing with the 3, 4, 5 triangle considering any angle. Okay? That is a 3, 4, 5 triangle. Now, if we are going to perform summation forces of y, we can say that negative w plus p cosine of beta is equal to 0. And therefore, w is simply equal to p cosine of beta. Okay? And then out of that one, we know that w here is how much? 1,500 kilograms. However, kilograms is a unit for mass. 1,500 kilograms. To make it a unit force, of course, we need to multiply it by 9.81 meter per second squared, or the acceleration due to gravity, because of course W is mg. We know that very well. Okay, so computing for W is actually 14,715 newtons. Okay, so we're gonna substitute that here, 14,715, and then cosine beta. Okay, where's that cosine beta here? This is actually beta. Okay, so let's place that by beta. Cosine is adjacent over hypotenuse. Adjacent to beta is 3 all over 5. Okay, so this is simply equal to 3 all over 5. So therefore, we can find here P, which is can write here 3/5 beside P, and then equate that to 14,715. So P, simply by cross multiplication, we have 14,715 times 5 all over 3. So P is 24,525 Newton. So what will be the next step? Okay, so after getting P, of course, we will now proceed to the FBD of AB. And remember that AB has a weight also. Okay, so where is the weight situated? So it is actually at the mid span. Okay, and it is also vertically downwards. That is equivalent to, according to the problem, 300 kilograms. Okay, so we have here 300 kilograms. Of course, again, we multiply it by 9.81 to make it a force. Then we have 2,943 newtons. And then if you observe again your FBD of AB, so it is just simply to take moments at A. Okay, summation moments at A is equal to 0. Okay, so summation moments at A is equal to 0. We have first P, that is a clockwise. P times the moment arm. So let's see the dimensions here. It is actually 2 meters from A. That is along the axis of your inclined bar AB. So that is 2. What else? Your weight is actually, again, we'll have a clockwise rotation. So we have 2943 times, you can see here that this is just 3 meters, and bisecting that one at the center, you'll just have 1.5 meters. Okay, and then TBC will go into a opposite rotation, so that is negative TBC times moment arm is obviously equal to 4. So this is equal to 0. Okay, so all we have to do is to substitute what we have obtained on P. So therefore, TBC is now the unknown. So we have here 13,366.13 Newton. Okay, so after getting TBC, of course, we are concerned with the tensile stress. So stress is simple. P over E. So stress is 13,366.13. So we have a cable which is 20 millimeter in diameter. Okay, 20 millimeter. So this is squared, and we have here sigma equal to 42.55 megapascals. Okay, so that's for the first one. Okay. Stress in the cable. Okay, so the next unknown is determine the weight of the heaviest cylinder that could be placed in the system if the allowable stress in the 20 mm diameter cable is limited to 30 megapascals. So assume weight of the bar equivalent to 300 kilogram. So this time the given are just jumbled. So the given now will be transferred, or the known figures are on the cable itself, and then the unknown variable here is the weight of the heaviest cylinder. So we can refer to our previous solution. Perhaps we can compute for our allowable on the cable, or the tensile limit, by simply using this formula, P over E, to your cable BC. Okay, so your cable BC is 30 megapascal. So we have here 30. Okay, we can replace this by tension at BC, and then area 20 mm, diameter. Okay, this is squared. So therefore, the tensile limit of the cable is equal to 9,424.78 Newton. Okay, so what is the next step? So in this case, we have combined or merge this BC in to the area to come up with the stress in the cable. So this time we are going to reverse the procedure, knowing that we have here TBC. So going back to the root solution here, as the first solution is at the FBD of the cylinder, you do not have the weight. Of course, we can use again by summation forces Y, but we do not place a value for W here, and P is for the component, vertical component of P is 3/5 of P, and then W is 3/5 of P, and then this summation moments actually involves P here, so therefore W should be in terms of P. Okay, so I hope that is clear to you. So we'll just have to solve P here, solving for P. P is equal to 5W all over 3. Okay, so P is 5W all over 3. So again, if we wanted to have the W, then again we take moments at A is equal to 0. So doing that, again we have the same equation will be formed out of this. So we have this one, but we're not gonna placing a 24,525 here. Okay, perhaps you can just copy this equation. Okay, but we do not place P derived from an equation placing a value for W. So 2943 obviously is the weight of the bar. It retains as it is. Okay, so TBC, instead of replacing P here, we're gonna replace a value for TBC because we have already have a limit for that, 9424.78, 9424.78, and then P is in terms of W, 5W all over 3. So as we can see here, this very clear that we can right away get for our unknown W. Okay, so we will have 9,985.38 Newton. So if we observe that in the first problem, okay, our W is given to be equal to 1,500 kilogram, and actually if we multiply this by 9.81, we have 14,750 Newton. So with this weight, it has a corresponding stress on the cable. Okay, the direct effect is on the cable. So the computed sigma for CD is 42.55 megapascals. Okay. Now, for the second unknown, we have set the sigma to be equal to 30 megapascal. So remember, 30 is less than 42.55. So therefore, it is expected that W will also have a lower value than 14,715. And the computed value for W was 9,985. Okay, so see, we have obtained the values, but the approach is the same, only that we have some sort of reverse engineering for rotating given and rotating unknowns in the problem. So that's it for this particular problem. Okay, so moving on to the next problem. Here we have three members that are pin connected. Okay, so by the way, this should be supported by a pin and a roller. Okay, so what is the maximum value of P if we consider an allowable tensile stress of 14,000 psi, and we consider an allowable compressive stress of 11,000 psi. So in dealing with the trusses, of course, you need to establish your angles. So that's so basic. So in this case, we have three sides are given with but no given internal angle. So normally we resort to a cosine law being applied and then determine your angles here. But if you are observant, we can see here that these dimensions are all divisible by 3. And if we're going to divide all those dimensions by 3, we can find out or simplify those dimensions that this is 4, this is 3, and that is just 5. And remember that a 3, 4, 5 triangle is just a right triangle. Okay. Okay, so this is 3, 4, 5 triangle. It is just a right triangle. Okay, so having that condition, of course, if we have P here, okay, so we need the distances here. Say this is 15. We do not know yet this distance, that is x, and the excess here is 15 less x. Okay, now we start to name the angles. Say this is theta and this angle is beta. So why don't we need these dimensions? Why? Because of course we are going to take moments to obtain the reactions, and these reactions shall be in terms of P. Okay, so there will be RA here in terms of P and the reaction at B. That is why we will be needing to determine the value of X. So how shall we do that? Okay, so since we know that this is 90 degrees, okay, and we also have some of dimensions here, perhaps you can stick to the original dimensions. Say this is 12, this is 3, and sorry, this is 9, and this is 15. So considering the whole right triangle and taking theta as our reference, we can simply write here tangent theta, and opposite to theta is 9, adjacent to theta is 12, so therefore theta is equal to 36.87 degrees. Now beta is just simply equal to 90 minus theta, and that is 53.13 degrees. Okay, so knowing all the angles, we are now ready to determine x by considering two right triangles on opposite sides of this larger triangle. So of course this is already bisected, so we know this one, this is already acquired, 36.87 degrees, and this is 12, this is 15 less x, and this will be our right angle now formed out of this bisecting line. Okay, so we can now write what function. So 15 minus x is adjacent and 12 is the hypotenuse, so therefore we're gonna use cosine. 36.87 adjacent is 15 minus x all over hypotenuse 12, so we can get here x. So x is obtained, which is equal to 5.4 meters, and 15 minus x is 15 minus 5.4, which is 9.6 meters. Now we are ready to take moments at both supports. Say this is point A and that is point B. So summation moments at E is equal to 0. We have say this is RB and that is RE. We have this as P. We have P times 15 minus x. By the way, this is x. Okay. So that is the dimensions. So what is 15 minus x equal to? 9.6. Okay. Minus 15 RB is equal to 0. So we have RB is equal to 0.64 of P, and you can now take moments at the other support. So negative P times x, x is 5.4, and then plus 15, RA is equal to 0. So RA shall be equal to 0.36 of P. So of course, as a check mechanism, all the downward force is just equal to P, and the upward force is 0.64 of P and 0.36 of P, so therefore we'll just yield to an equilibrium along the vertical axis. So now we are ensured of our reactions. RA is 0.36 of P and RB is 0.64 of P. So we'll just have our analysis. Okay, so this is 90 degrees. Okay. So what is RA? 0.36 of P. And RB is 0.64 of P. Okay. So what shall we do with this? we will take bisection method. Okay, we can do that by force triangles in each of the joints. Say we have A, this is B, and that is C. We'll just have to illustrate here a force triangle for the diagonal member. Okay, so the very first step in method of analysis, we're going to choose a joint where there are only two force members. Okay, so all of the force members are 2. There's P here. So we can choose from a joint that has a given. Okay, a joint has a given. Of course, kung pipiliin natin yung C dito, there will be no, we can get nothing but a bunch of unknowns. But on A, we are having a reaction of 0.36 of P, which could be the basis of the diagonal force AC. Same true with BC. So in short, we can choose either AC or BC for our convenience. So this time I am going to start with joint A. Of course, this is going upwards. So if we take this joint, of course, we need a balancing force that is also going downwards to counter here 0.36. And as we can see, this member AB has nothing to do with the vertical. Remember that? Okay? Has nothing to do with the vertical. So therefore, AC will be the only member to counter the upward 0.36p here. So therefore, ibig sabihin na yung AC, dapat yung AC, kina-counter niya yung going upwards dito. Okay? Yung AB, hindi naman pwedeng vertical yan because it is set or fixed on the horizontal. That is why AC is the only force to counter this one. And when that happens, dapat yung direction nito, it is obvious that it should be towards the joint so that its vertical component will be equal to 0.36 of P. Okay, that's it. And then if we know that one, we can now determine AC X, or the component of AC along X. And of course, eventually, the value for AC. So what is our reference here? Of course, we're going to refer to the slope or the angle. So this time, I'm going to use the angle. So we have an angle there. It's 36.87. Okay. So all we need is to refer to the triangle and the simple trigonometry. What do we know here? Okay, we know this. So intend to get this one. So what function? Tangent. Okay. A tangent 36.87 degrees. Opposite to that angle is 0.36. Adjacent is ACX. And hence, ACX will be computed directly. in which ACX is found to be 0.48 of P. So we can place it here, 0.48 of P. Now we have obtained two legs. Of course, this can be easily, or AC could be easily obtained by applying the Pythagorean theorem. It is just equal to 0.48 squared plus 0.36 squared. Okay, and that is found to be 0.6 of P. Alright, now at joint A we have already balanced what? The vertical only, but at this point in time the horizontal one is yet to be balanced. And what could be that balancing force and what should be balanced? Okay, because of this compressive force AC, there will be a 0.48 going to the left. Okay, so if we have this one 0.48, a leftward force going to 0.48, and this time we do not have any force, so therefore the force member AB is the only force to balance that one. So therefore we can place here a rightwards balancing force, okay, for this 0.48. So this should be equal to 0.48 of P. Okay, so we will do the similar procedure to this. Okay, so what is the balancing force here? Of course, this must be compressive in nature, so that the vertical here shall be equal to 0.64 of P. And if we consider the angle here, say this is 53.13, 53.13 degrees, then we can obtain CBX by a simple tangent function opposite to that is 0.64 of P, and then we are after with the CBX, and CBX is equal to 0.48 of P, and actually we can place it here, 0.48 of P. And if we notice, it coincides with the 0.48 going to the left, okay, and 0.48 going to the right for this diagonal member. And CB, the member CB, would be right away derived by the square root of the squares of the two legs plus 0.48 squared. So therefore CB is 0.8 of P. So let us now summarize the force members. Actually, there are only three force members. The members AC, member CB, and member AB. So the orientation, say this is the magnitude, say in terms of P. So the orientation of AC, what is the orientation? The force is towards the joints. So when it is towards the joint, that is in compression. Okay. And then CB is also towards the joints. So therefore that is also compression. And then AB is away from the joint, so that should be in tension. Okay, so for the magnitude, AC is 0.6 of P, CB is 0.8 of P, and we have here 0.48 of P. And then we take note of the allowables. What would be the allowables? So if we consider an allowable stress of 14,000 psi, tensile stress is 14,000 psi. So sigma tensile is 14,000 psi. And then sigma compressive is equal to 11,000 psi. And then we will be concerned with the cross-sectional area. So in this case, we do not have an area, so it is supposedly given in the problem. Say in this problem, let us set our area to be equal to 2.88 square inches. So using that, we can now determine the value of P. So in tensile, so at least we can have these all areas to be equal to 2.88 square inches. So considering sigma under tension or tensile stress equivalent to 14,000 psi, we'll just have to consider this one. Okay, so we only consider this because these are both in compression, so we cannot apply this allowable because it is intended only for tension. So therefore, by simple formula, sigma is equal to P all over A. Okay, we have 14,000 for the allowable, and then the magnitude of PAB is 0.48 P. By the way, just place here for AB. So this one is actually PAB, and then area for AB 2.88 for all the areas. Okay, so by cross multiplication, we can solve for the value of P. So P will be equal to 84,000 pounds. Okay, so this is the answer for a P that is considering the allowable tensile stress. And then for allowable compressive stress, we can consider both of these, but we cannot use this one. Okay, so first, let's apply this formula for member AC. Okay, so for member AC, we have the allowable that is fixed to 11,000, and then this is 0.6 of P as the value for PAC, and then we have here 2.88 for the area, so that we'll be having a value of 52,800 pounds. Okay, so we're gonna do the same for the member CB. Okay, this is fixed at 11,000, and then CB is 0.8 of P with an area of 2.88, And by the way, that is the actual force at CB, and therefore P here is equal to 39,600 pounds. So those are the values of P. First, if we're going to consider the tensile allowable, and this is for the compressive allowable. So a follow-up question would be, among these three computed values, what will be the safe value or the maximum value of P? So the tolerable one is always the lowest, as we have discussed on the previous session. Okay, so that's it for the solution of the three problems on your seat work. So please stand by for the lecture on the next topic. So thank you for listening, and see you on the next video lecture.